by our Pakistani researchers working abroad. So we have Dr. Muhammad Rizwan Niazi working on organic semiconductor transistors from McGill University, Canada, joining us. So Dr. Rizwan Niazi, I hope you're all ready to share your presentation with us, please.
Thank you, Yajan. Thank you very much. Yes, I can share my screen. Is it visible?
It indeed is visible, but you need to do the slideshow.
Yeah, I'll go into that. Don't worry. Sure. Perfect. All right. Let me just. Thank you, Yajan, for arranging this talk. And before I begin my presentation, I would like to thank and congratulate all the organizers for this great initiative. And I would like to welcome all the guests, all the participants for being part of this wonderful initiative to promote applied sciences in Pakistan. Thank you very much once again. I would like to speak about organic semiconducting thin films for field effect transistors. I typically work with a lot of material systems like perovskites for solar cells, organic solar cells, organic diodes, polymer solar cells, polymer transistors. Today, specifically, I'm going to talk about organic small molecule based thin films for field effect transistors. I would begin by introducing you with the field before showing you the key research objectives of the work that I did in past few years, and then I'll conclude in the end. So the concept of field effect transistor was introduced by Lilienfeld in 1925. He was unable to make a working field effect transistor due to some technical issues. But later on in 1948 at Bell Labs, Shockley and co-workers, they presented first working field effect transistor. Later on in 1959, Egyptian engineer Muhammad Abdullah and a Korean engineer Devon Kang, they were the first ones who invented metal oxide semiconductor field effect transistor. According to US Office of Patents, this was the groundbreaking invention that transformed life and culture around the world. And as you can see, all the electronic devices around us are based on these devices. So this statement was absolutely true at that time. All these discoveries were made with inorganic materials later on in 1977. An important event happened that Professor Heger and colleagues, they found that plastics, polymers can also conduct electricity. And because of this discovery, they were awarded Nobel Prize in Chemistry of 2000. After their discovery that polymers can also conduct electricity in 1977, 10 years after that time, a first organic thin film transistor based on a polymer semiconductor was presented and reported. So this, after giving credits to the pioneers, the organic light emitting diodes based electronic displays which are being used in TVs and smartphones, this is an established and successful example of organic semiconductors in today's era. And according to this ID TechX report, by 2030, the organic semiconductors will have around $65 billion market across the world. The other major applications of these materials are basically in thermoelectrics, organic solar cells. These are still under development. As far as the organic field effect transistors are concerned, they find multiple applications in different areas. For example, I can name few. These can be used to drive the front panel OLED displays. They can be used as electronic papers in memory devices, in radio frequency identification tags, etc. Importantly, these devices can be used as gas sensors, chemical sensors, and biological sensors, and it can detect everything depending on their functionalization. The main idea behind it is basically to move away from rigid, brittle electronics and move towards foldable and stretchable electronics, because organic semiconductors are flexible, they are solution processable. Specifically, the polymer semiconductors, they have superior mechanical properties as compared to their inorganic counterparts. So, what is the working principle of these devices? So basically, as you know, the transistor is a core component of any electronic circuit. It is a three-terminal device, field effect transistor, specifically the three-terminal device with gate, source, and drain. The electrical conduction can be modulated in the semiconductor layer by an applied variable electric field between gate and source electrode. The charges upon application of this electric field are accumulated at the organic semiconductor and dielectric interface, and then these charges move through this interface by an applied constant potential between source and drain. The performance matrix of this device can be evaluated by two types of current and voltage characteristics, named as transfer and output. I won't go into the details, but the key figure of merit here is the charge carrier mobility, or the field effect mobility, which is nothing but a drift velocity of these carriers under applied field. So in past 3-4 decades, what happened that there is a tremendous improvement on this figure of merit, which is mobility, because of combined breakthroughs on process engineering, molecular engineering, and interface engineering fronts. Combination of all these three has enabled organic field effect transistors to be applied in various technologies such as OLED, which has a minimum requirement to be driven by OFETs having mobility of 10. So how we can process these materials? So basically there are two different methods: vacuum processing or solution processing. Vacuum processing requires complex equipment, it's costly. On the other hand, in case of solution processing, these materials basically are designed in such a way, molecularly tailored in such a way that they are soluble in common organic solvents. So once you mix them with common organic hydrocarbon solvents, they dissolve and they become a functional ink. The different colors are definitely due to different band gaps of these materials. Typically, once you have this ink, you deposit them either using lab-based processing techniques such as drop casting or spin coating. But as these are not compatible with roll-to-roll printing methods, over the period of years, new coating techniques, which are called meniscus-guided or other printing techniques, have been developed to print or coat these materials in a way so that the future printing at industrial scale is compatible with the research scale efforts. So once you have the ink, you use a method to deposit it on a substrate, appropriate substrate, and then you complete the device by depositing other remaining layers of the device, and then you evaluate the performance of this device. So the performance overall of this device is coupled with the method used to deposit the ink thin film on the substrate, which is dependent on the recipe that you use, the choice of the substrate, the interface properties, or any kind of post-processing step that you use. And all these things eventually control the solid state structure, which is molecular orientation of molecules in the solid state film, the degree of defect state, the microstructure, the crystal structure, etc. So overall, the performance of such a device is basically linked with solution processing and solid state structure. So understanding this phase transformation process is key to control the crystalline, polycrystalline thin film quality to eventually dictate the device performance of organic semiconductor based thin films. So with this background, I would like to say when we started this research like 4 or 5 years ago, the plan was to understand this phase transformation process, because at that time there was no study or data available to provide the information or the required knowledge to dictate the solid state structure by understanding this ink to thin film phase transformation process of organic small molecule semiconductors. So build few setups to understand this using time-resolved high-speed optical microscope and time-resolved X-ray scattering experiments at synchrotron source, and some in-situ thickness measurements and some other experiments. And we use this knowledge and develop efficient protocols to eventually control the thin film quality. And combining all this, we targeted to manufacture these devices at industry compatible manufacturing conditions. To begin with, I would like to show you when we started these experiments, we used this high-speed camera, we coupled it with the coating setup, and the first example that I want to show you is of conventional lab-based spin coating process. So when we deposited this ink through spin coating, these images are taken from a movie recorded using the high-speed camera. We found that the nucleation events, the second image, the nucleation events begin while there is a clear signature of liquid, while there's a clear signature of a solution present because of these interference fringes. If we move towards the industry-compatible coating techniques such as blade coating, which actually have different coating regimes at low speed, what we observe the formation of highly textured and oriented crystals propagating at the meniscus edge with the moving blade, while at higher speeds we observed a stochastic nucleation process happening from in the extended meniscus. So these two phase transformation processes, or the thin film formation processes that we are seeing, are totally different what we observed earlier. To understand this phenomena in detail, we went to Cornell high energy synchrotron source. We developed the setup, we coupled it with the coating systems, and in the end what we found, we observed basically two things: the evolution of solution signal, represented here in red plot, and the green one, this is coming from the diffraction of crystals of this material. So basically, as you can see in conventional process, the spin coating here, there's an overlap of solution and crystallization signal. While in case of blade coating, the solution signal first fades away, and after some time we observe the evolution or the onset of crystallization. And when we monitored the thickness evolution during these two experiments, we found that the concentration where onset of nucleation happens for the case of spin coating or conventional process is basically very close to the solubility limit of this material at room temperature. While in case of blade coating, we observe that the onset of nucleation happens when the concentration is approximately close to 90%. So these two observations actually suggested that this extended meniscus, first of all, is an amorphous phase because we did not observe any crystallization signal. The second thing is highly dense. There is a very tiny amount of solvent left in this, and combination of all these three, high-speed, polarized optical microscopy, the grazing incidence, wide angle axis scattering experiments, thickness experiments, basically pointed that the small molecule organic semiconductors can be crystallized through an amorphous, dense intermediate phase, which we name here as a quench phase. So if you evaluate the quality of these films processed via conventional method, which is spin coating, or meniscus guided technique, we found through atomic force microscopy images that the films are more compact, there is a less density of defects, and the surface roughness values were much lower in case of the films processed through this quenched intermediate phase as compared to the conventional process. The X-ray diffraction experiments showed the higher or improved lamella quality in the second case, the quenched intermediate case, and the devices based on these two films were remarkably different. As you can see in this top plot, that there was a 1 to 2 order of magnitude difference in the charge carrier mobility from based on different based on the films processed through quenched intermediate phase. When we analyze the density of states in the band gap of this material using the current voltage characteristics, we found an order of magnitude decrease in the trap state density. Similarly, the photo deflection spectroscopy also showed lower Urbeck energy values, which actually is correlated directly to the energetic disorder in the film, suggesting that the film processed through this intermediate quenched phase has a smaller energetic disorder. Then we asked ourselves, is this phenomena generalizable or not? We took 3-4 different small molecule organic semiconductors, and we did different experiments, and we found that yes, the phenomena is absolutely generalizable. All the materials, when processed through these meniscus guided techniques, they go through this amorphous, dense intermediate phase proven through high-speed optical microscope, the time-resolved grazing incidence, wide-angle X-ray scattering experiments, and the XRD, the atomic force microscopy. They all prove that the film always have superior quality as compared to when processed through conventional methods. One of the important findings that we observed was that in case of conventional processing methods, we always had two different molecular texture in the film. One is called face-on and the other is edge-on. The face-on texture suppresses the pi stacking, in-plane pi stacking that is necessary to have a better charge transport properties in these devices. While in case of films processed via this quenched intermediate phase, only had edge-on texture, which promotes the in-plane pi stacking and then eventually promotes the in-plane charge transport. Further detailed investigation of peaks, we found that always the films processed via conventional methods, the peaks were smeared, and detailed analysis always showed that the in-plane peaks, which are directly correlated with the in-plane charge transport, showed higher signal intensity for same film thickness, which 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 suggested that the improved charge transport properties that we were observing earlier through devices were basically because of this improved microstructure in the solid state thin film. So we were basically controlling the microstructure of thin films using this intermediate quenched dense phase. Before I conclude,
Dr. Niazi, yes, can you please conclude?
Yes. Before I conclude, I would skip this example. I would jump to the second example before the last slide. So then we used we generalized all this knowledge and understanding to the best available small molecule organic semiconductor, which is called C8BTBT. Conventionally, when it is processed, it shows massive nucleation density, defect density. Typically, it is melted first at 125 degrees Celsius, cooled down under careful conditions to basically increase the domain and crystallite size, and then the performance jumps up. What we did, we applied all of our knowledge. The material goes through different mesophases. I won't go into the detail, but eventually we were able to show that this material can also be processed through this quenched amorphous intermediate phase, and the performance of this film eventually is on par with the melt processed films, or in some cases it is even better. And the grazing incidence wide angle X-ray scattering experiments showed exactly the same thing that we observed earlier for other materials. In conclusion, I would say that we found that this amorphous quenched intermediate state is key to control the organic small molecule semiconductor thin film properties when they are processed through meniscus guided techniques. We developed protocols eventually to basically coat thin films based on small molecule organic semiconductors at industry compatible coating speeds of 100 millimeters per second with charge carrier mobility of more than 10 centimeters square per volt second. With this, I would like to acknowledge this work basically was part of my PhD thesis. I haven't shown my post-PhD work due to time constraint, but I would like to acknowledge University of Kentucky, King Abdullah University of Science and Technology located at the shores of Red Sea, Cornell High Energy Synchrotron, Wake Forest University, University of Brussels, and all the collaborators throughout this work, and my PhD advisor, of course. With this, I would like to thank all of you for listening. I'm open for all of your questions. Thank you.
Dr. Niazi, that was a wonderful talk full of very nice photos, atomic force microscope images, and wonderful studies. We congratulate you for such a wonderful work and wish you all the best. We have time only for a couple of questions, perhaps. So among the attendees, anybody who would like to ask a question, can you please raise your hands? So I'm allowing Muhammad Arshad to please go ahead and ask your question. Muhammad Arshad, over to you. Muhammad Arshad, can you hear us? Can you please ask your question?
Hello, can you hear me?
Yes.
Yes, thank you so much. So, thank you so much for a wonderful talk. I'm Mohammad Arshad from National Center for Basic Studies, University of Islamabad. So, my question is regarding to the growth process. Can one also do the seeded growth? I mean, put some seeds for nucleation on the substrate before you did our process like that?
Yes, Arshad, thank you very much. Yes, that is very common, So we call it as a growth via nucleating agents. So you add those whether in the solution, whether in your functional ink, or you pattern your substrate in such a way that you have a heterogeneous nucleation. But In case of small molecule organic semiconductor, it's because it's crystalline, so you don't want any kind of heterogeneous nucleation. Though there is always heterogeneous nucleation from its own, but we don't want any heterogeneous nucleation. What we want is the larger crystalline or grain size or the domain size, so that we can avoid the grain boundaries in our thin film in a device channel, which impedes the charge transport properties of these films. But yes, back to your question, yes, it is possible. People are doing it for different purposes, and it is absolutely doable, already done.
Okay, thank you, Dr. Niazi. So I will allow only one more question because of time constraints. So Dr. Muhammad Ramzan, over to you. Can you ask your question to Dr. Niazi, please? Dr. Muhammad Ramzan, you've been allowed to talk.
Hello.
Yes, go ahead, please.
Yes. Thank you, Dr. Rizwan, for such very nice and informative talk. I have a question that how you did measure or maintain the thickness during blade coating?
Yes, so basically we are using the reflectivity measurements.
Okay.
Yeah, there is a very famous company, Filmatrix. They have equipment, and you can use either it for regular transmission measurements, for UV rays absorption, or you can use it as a reflective measurements, and then you can basically back calculate using the optical constants the film thickness.
Thank you very much.
Players.
Dr. Niazi, it was wonderful to have you here with us, and we thank you really for the very nice and very graphic talk. And this is the spirit of the conference, basically, because you wanted to show the audience a broad picture of what people are doing rather than being very specific. And I really liked your talk because it resonates with the theme of the conference very well. So we should connect in future, hopefully. But for now, I bid you farewell from here, and I'll go to our next.
Thank you very much. Thank you, Yarjan. I really appreciate. I tried to be as simple as possible, but if people have questions, they can always approach me. Thank you very much.
I think people can connect with you. Thank you, Dr. Niazi. Thank you. So with Dr. Niazi's talk being done,